when you have followed my channel, you will surely know that I was busy to make a VLF radio. And in the past only, say, with a long wire antenna of approximately 10 meters or 15 meters hanging in my garden. But of course I'm more or less inspired about this radio. And this radio is a simple transistor radio of the 1980s, and I found that it has a very good long wave radio reception. Of course, we know when we look at such a radio that this is the transistor end stage. This is a medium wave ferroceptor, the ferrite antenna, and this is the long wave part of the ferrite antenna. And say you can move that coil on that ferrite antenna to get the best proper radio reception, and they have done that, of course, in the factory. So the aim of this video is coupling of VLF coils. It's only a vlog. I don't show any schematic. By the way, the schematic of the thing that I use here is the test oscillator, was already on YouTube on my channel. And my idea was that I could mimic here in a certain way this antenna coil for VLF. And I think I'm on the wrong side, because when I studied this, it has so much more windings, and I know, of course, like every radio amateur knows, that it was made with so-called Litze wire. This is Litze wire, and it has, say, 20 or more strands of extremely thin wire. Has everything to do with a skin effect, so-called skin effect in radio reception. You can Google it anyway. But so I think this thing does not mimic in terms of radio reception, not in terms of frequency generation, the reception coil for VLF here. Anyway, going on with my struggle to, say, reproduce this very simple medium wave and a long wave radio in a certain way. Of course, it's a super heterodyne radio. There's a local oscillator here. There is a first stage, must be here somewhere with this transistor. This is, of course, say, the classical end stage of these old school transistor radios. Two mini transformers. I think it's a push-pull circuit here, more or less sure. Here we have two transistors that do that job, push-pull, and such a push-pull circuit is very good to work on low supply voltages. Anyway, that's a low frequency part of the radio. Here's the high frequency part of the radio anyway. Well, I lay it aside, and here is, by the way, my first experiment for long wave. I receive it on a long wave antenna hanging in my garden, a wire antenna of approximately 10 meters, but well, anyway. This proved to be, by the way, so that long wave wire antenna differs completely from this other antenna on that ferrite rod. It acts on the magnetic field of the radio station, and the long wire antenna more or less on the electrical field. Anyway, this proved to be quite good long wave coil. It's only a vlog now. I don't publish schematics, etc. But by the way, this was on my YouTube channel, and when you have followed my channel you will surely know it. This is my test oscillator again, and say now it's about the coupling of VLF coils. Say this is the transmitter coil. It sends out its frequency here. It's on 149 kilohertz. When I, of course, push in the ferrite rod here, we go to lower frequencies. So 125 kilohertz. Now I take it out. Let's see what happens. Amplitude changes, by the way, but also the frequency, and that's more important. Say the amplitude changes are not very fierce anyway. Push it in again. So. But now we have here this situation. This coil is the transmitter, and this coil is the receiver. It's 250 windings, as far as I know, 250 windings, and you can also very thin wire, and you can also stick in that ferrite rod, so you can tune this coil, the reception coil, to the transmission coil. Let's see what happens. Now we are on 15 kilohertz. I take the rod somewhat out. And I take the rod, I have to take a much distance, otherwise I cannot show it. I take that rod out, it's now 194 kilohertz. Take the rod out, and here there is, say, a certain situation where these two coils here and here couple in a proper way. We even see, very strange by the way, but it has also to do with the settings of my scope. So that's my conclusion afterwards. We receive here a quite good, here, that's here, in this reception coil, a quite good signal. Now I say take out the ferrite rod of the reception coil. Let's see what happens. So we see surely that it doesn't receive any longer that fierce frequency. Now I push it in again. So here is the resonance peak. So the best resonance peak is here. I move it now in and out. So now it's more or less at its maximum, and that means that this coil is tuned to 211 kilohertz. Important to tell is that this is connected here to an oscilloscope. The oscilloscope has an input impedance of approximately 1 mega ohm, and this scope, by the way, 1 mega ohm, and in general something in the order of 10 picofarad up to 20 picofarad, and that means that we have here two sources of capacitance that bridge the coil, and that is the oscilloscope capacitance and the internal capacitance that is generated between all the windings here when they are closely wound, and they are of course isolated. There is a kind of natural, say, capacitance between all the windings. It's 300 windings, by the way. So I hope it was not very boring. Well, perhaps I can show some other phenomenon. I push in the rod to the transmission coil, so it means the frequency goes down, and here you can see that the amplitude gets up at the same time. let me show it again. Here, I have to take so much distance, by the way. Push that rod in. You see that the transmission coil here on 118 kilohertz sends out a fierce energy, but of course we have to tune in here in the reception coil to get to the same frequency. And well, does that succeed? No, it does not succeed. So even when I move it here, it does not succeed. That means that this coil cannot be properly tuned to that low frequency of 118 kilohertz. My camera starts flickering, so I have to take it. Here we see the same circuit again, but now it means, of course, that these two coils, this is the transmission coil, reception coil, they are, say, tuned properly. Again, move that ferrite rod in the reception coil in and out, and again we have here the proper reception. The distance, by the way, between these coils is approximately 75 centimeters. Anyway, here the transmission, here the reception, and of course when we move them closer together, the energy out of the transmission coil can be transported in a much more fierce way. It weakens here through the air, through the atmosphere, and of course when we are talking about radio transmissions on VLF or M-wave or high frequencies, this is also, say, the normal thing. That's what I wanted to say. Let's tune again to see what happens. Very, very interesting in my opinion. But anyway, the big advantage is, like I told, to mimic this radio. Make it in my own way. And perhaps, yes, surely, perhaps I surely have to use Litze wire finally, but I don't want to do it, but because I always want to make all my circuits very easy to be reproduced. And Litze wire is expensive, and perhaps even nowadays, 2024, not very easy to buy. Not very easy to get. Thanks for watching.